Hi, I'm Chris Kanish, and this is CS361, Systems Programming. Today, we're going to be talking about programming with sockets. The TLDR here is that programming with sockets looks like this. You got a whole bunch of different calls. In some ways, it's very similar to programming with files, where we're reading and writing files, but there are a lot of very important and relatively subtle differences. The first thing that we want to recognize here is that there are two ways to communicate using sockets. You can communicate as a client who makes a connection, or you can communicate as a server who receives connections. The way that we set this up is going to look very different whether we're on the client side or whether we are on the server side. So on the client side, there's one call that's specific to the client side, and that's connect. This is called an active open, where a client decides it wants to receive service from a server, and so it goes and makes that connection to the server. This is not super important at a purely technical level, but at a semantic level of who should be the server, who should be the client. The client is almost always going to be the one who makes the connection because they decide, oh, hey, I want to get some service from somebody. I'm going to look them up in the DNS, I'm going to make a connection to them, and I'm going to ask them to do something for me. This isn't always going to be the case. There are some protocols where you are both connecting to and being connected to, like SMTP or BitTorrent. But in general, and at a technical level, this is an important distinction for socket-based programming. Likewise, on the server side, we need to set up our system so that we can receive those connections coming in from clients. There's a few extra things that we have to do to accomplish that I'll talk about in a moment. But once we have either connected or we've accepted a connection from a client, then everything works perfectly symmetrically. Either side can send messages, either side can receive messages, either side can close the connection saying, hey, I'm done talking to you. All of these things work effectively identically on either side. I'm using this diagram that I kind of repurposed from the book. One thing that I didn't change but is important here is that either side can cause the close to happen. Just because the client in this example called close first doesn't mean that in a different protocol or in a different run of this protocol, the server wouldn't be able to also say call close first here, which sends that EOF signal, and then the other side will also close. So let's go through each of these different calls that are related to using sockets and figure out what it is they're doing, what they're responsible for, and how they work. Getaddrinfo is a very important call that we use to leverage the DNS. This is the Unix function that we use to do DNS lookups. It allows us to input a host name saying, hey, I want information about this host name, and the DNS will be consulted by the library. We don't have to care about how DNS works. All we know is that we're going to get back a structure that gives us the information that we asked for. It might give us several different answers. It might give us no answers, but we are going to get that information that we can use to move forward in, say, connecting to a server. We also use getaddrinfo to figure out what our own server is and set up a structure that we're going to then pass eventually to bind when we get to it. But we'll cross that bridge when we come to it. So socket creates a file descriptor just like open does, but all it does is create the file descriptor. It doesn't connect it to a stream of bytes coming out of a file or a connection like open does. A file descriptor created by socket doesn't do anything. It doesn't even use the output of getaddrinfo. So this diagram kind of like the output of getaddrinfo gets sent to connect, the output of getaddrinfo goes to bind, but it doesn't actually come through here. We don't need it to create our socket. Stop me if it's annoying, but I love using analogies to try and get an idea of what this means in the grand scheme of things. I kind of think of calling socket as building a door frame that isn't connected to a wall or a house or anything yet. Like, yes, the door is there. I know I can put a name on it. I can save a reference to it. I know that I'll be able to go through it using the file descriptor I get back, but it's not connected to anything. If I try to send to it, if I try to walk through a door that hasn't been hung yet, I look like an idiot. And the C runtime will probably make you look like an idiot if you do that too by crashing. So the next call we're going to look at right now is connect. So connect takes as input a file descriptor that has been prepped using socket and the output of a getaddrinfo call and says, hey, I'm going to use TCP under the hood. I'm going to do all of these cool three-way handshake things and the SYN and the ACK and all of that stuff to set up a reliable connection on top of the best effort delivery service provided by the network layer. And all of the complexity of that gets abstracted away. We call connect, and the operating system takes care of initiating that connection for us and getting it ready for us to send and receive bytes. This effectively, in our analogy, installs the door in a house. We know how to use it. We know how to turn a doorknob and push it or pull it or whatever have you. But we don't need to know carpentry, right? We don't need to know how to hang the door. We don't need to know how to put the nails and the screws in. We don't need to learn about any of that stuff. All we need to know is, yes, tell the GC to put it in there, open the door, you're in the house. Fantastic. And finally, both on the client side and on the server side, we're going to be using these system calls called send and receive. They're really, really ridiculously similar to write and read that we have for regular file system calls. And sometimes you can actually even use those. But the really important thing to remember here is that what send and receive do is, given a file descriptor and a collection of bytes, tell the operating system to attempt to deliver up to this many bytes, or tell the operating system to give you up to this many bytes out of the buffer where it holds messages it has received, or into the buffer where it holds messages that it's going to try to send for you. It's incredibly important to remember that the moment you have called send, all you've done is told the operating system, hey, please deliver this for me. If the operating system comes back and says, okay, you gave me 1500 bytes and my return value is 1500, that does not mean that those 1500 bytes have hit the network and gone out. That does not mean that the server has received them. All it means is that the operating system has received those messages from you and will do its best to reliably send them to the other side. We cannot stress this enough. Send and receive do not do the sending and receiving themselves. They only allow you to ask the operating system to give you what it has received or take things and send them eventually. And finally, close takes a connected file descriptor and tells the operating system to shut it down. This is a kind of special flavor of send you could kind of think of, where it's sending a special message saying, hey, I'm done talking to you, please go away. The kernel is going to continue sending bytes. If it hasn't sent everything that you gave it with previous calls to send, it's going to keep trying to send those. And then it's going to send a special signal to the other side saying, hey, conversation's over. We're not sending anything else. We're not listening to anything else. Goodbye. The way that you receive the fact that a close has happened is you call receive and you get back a 0 byte length response, which is kind of a fancy way for the C standard library to signal to you, hey, the only time you would ever successfully get 0 bytes is when there's nothing left. And that allows you to say, okay, yes, this connection is closed. I can close it on my side and go move on to whatever else I wanted to do. Switching over to the server side, there is this collection of 3 different things that we need to do, right? It was easier on the client side because all we had to do was an active open, connect to the server, we run connect. As soon as that returns, we're ready to start sending and receiving, but it's not as easy on the server side. On the server side, we've got to do these 3 different things in order to successfully create a server and start a conversation with a client. So the first thing that we're going to do is bind. So given a file descriptor that we've created using socket, this tells the kernel to associate that file descriptor with a specific IP and port that that computer has access to. The reason we need to do that is that we want to reserve it for ourselves. Like if I was redesigning this API, I would probably rename it to something like reserve because that makes a little bit more sense. We're asking the operating system, hey, please make it so that only this process I am, can receive messages on this IP and this port. I don't want anybody else to receive messages on it. I want to receive messages on it. So an analogy here is that you're making a reservation at a restaurant. You call ahead to make sure that they have a table for you. If they don't have a table for you, you can say, oh, well, I'm going to go to a different restaurant. I'm going to get a different port number, whatever have you. But I can't use the same port number as somebody else because it gets reserved only for that user at that moment in time. The next step is telling the operating system to listen. And this is where it gets a little bit more confusing because, yeah, it makes sense that you have to bind something. But the 2 things here, listen and accept, get a little bit trickier. So given a file descriptor that has been bound, tell the operating system that you wish to start receiving connections. This is analogous to like taking that open, the close sign and switching it over to open. What you're doing is saying, hey, operating system, I reserve this port and I want you to start accepting connections and doing the synchronization and all the stuff you need to do when people try to connect to this port. This basically says this port is open for business. What's really, really important here is that saying this port is open for business is not the same as letting somebody in the door. So accept is analogous to like a doorman telling the client that they're allowed to walk into the store. And then once they've walked into the store, they're going to start talking to the shopkeeper, which is your user level code. So accept is very, very interesting in that after you have called bind, after you've called listen, telling the operating system to start receiving connections, then we can call accept to start one conversation with one client. Accept is going to return a new file descriptor that is different from the file descriptor that you've been using this whole entire time. So there's going to be a server FD. So you receive that from the call to socket. Come on, here we go. You pass it into bind, you pass it into listen, and you pass it into accept. Bind and listen are both going to give you a success or failure result. Accept, if it is successful, is going to return to you a new file descriptor that is connected to one specific client. This server file descriptor isn't really for sending and receiving messages. It's only for accepting connections from clients. Once you've accepted a connection, you have a new file descriptor. And it makes sense that you would have this file descriptor because if I want to talk to two different clients at the same time, I probably need two different file descriptors for it. So every time I call accept and it's successful, it creates a new file descriptor for me to talk to that one client. If I receive another client, I'm going to call accept again. I'm going to get a different file descriptor to talk to the second client. So I can talk to the first one through the first file descriptor, second one through the second file descriptor. It all works out, even if it is a little confusing when you're first learning it. Trust me, it took me a while. So there you have it. That's basically how you use the socket API for running a server or client, anything that's using TCP. In Unix, this is how you would be implementing a client or a server in that way. So what's so cool about the sockets interface? The biggest thing here is something we've seen already, specifically that these functionalities, once you've made that connection, are more or less identical to the way that the normal file interface works. So if we used a normal file to read and write, we can also use a socket to send and receive. We could even create that socket as a file in the file system, connect it to some other place, and it all works out the way we want it to. The main benefit here is that we're using this standardized set of APIs, and the operating system is going to take care of how to do the connections, how to do the buffering, how to do the retransmission, all of this stuff, so that all we need to worry about is knowing the tricky parts that we're going to see in a moment, and using it to build whatever application it is we want to build on top of the socket API. So the really, really tricky things that come out in using the socket API is really about absolutely positively needing to keep track of what the return values are, how many messages you've sent, how many messages you've received when you're trying to send a given buffer or receive into a buffer, things like that. You're only submitting bytes to the operating system. You're not actually sending them yourself. You can't say, oh, well, as soon as I've said send here, I can immediately close my program. Well, like if I close down my program as soon as I call send the last time, I don't have any guarantee that the other side has received those messages. I probably want to call close and wait for that close to return before I say, hey, I'm done, I'm going to close my program. And in addition, remember send and receive, their return values are going to be the number of bytes that were accepted by the operating system, either for sending or giving you. And if you're trying to send 1,500 bytes, you have to deal with keeping track of how many were sent. You have to keep track of the next time you call send, you start where you left off. You don't want to send too many, you don't want to send too few, you don't want to have a boundary error, kind of an off by one way or the other. You don't want to just send null bytes after null bytes after null bytes. You don't want to end up with a bad boundary condition on a while loop where you're infinitely sending messages as fast as you possibly can. All of these things are the various tricky things about socket programming that is made easier by the socket API because after you learn the ins and outs of these different calls, it's relatively straightforward to use. But you're always going to have these types of problems when you are using APIs that are as low level as this. These are effectively small layers of C code on top of the way that the operating system works. And that's what we're learning in this class. It's all about how the Linux operating system exposes its capabilities to the user level. It's another reason why we use C, because it's so close to the operating system, the way that it was built. That's all I have for you today on the Socket API. Thanks so much for watching, and I'll see you next time.